In the previous lecture, we discussed what charge is, where it comes from, and how it behaves at a very basic level. We stated briefly that like charges repel, while opposite charges attract. However, we did not discuss how strongly they repel or attract. In this lecture, we shall discuss exactly this. Specifically, we will quantify the force experienced by one charge due to another. To keep things simple to begin with, we'll start with two charged spheres, which we'll denote by the charges Q1 and Q2. We want to know the force experienced by one of these particles due to the other, and vice versa. In this example, we'll denote the force on Q1 due to Q2 as F12, and the force on Q2 due to Q1 as F21. In the 1780s, Charles Augustin de Coulomb proposed a simple expression for these forces. He stated that the force experienced by a charge Q1 because of a charge Q2 is F equals K times Q1 times Q2 divided by R squared, along the direction R hat. This expression is appropriately known as Coulomb's law. K is a constant known as Coulomb's constant, while R denotes the distance between the 2 point charges. This last symbol R hat is a unit vector, which tells us the direction of the force. We'll come back to this in a moment, and instead focus on the magnitude of the force, which is contained in the rest of the expression. First, let's talk about these charges Q1 and Q2. In the last lecture, we briefly touched on the elementary charge, E, which is the charge of a proton, and minus E, which is the charge of an electron. In objects on a human scale, which might contain, say, 10 to the power 23 electrons and protons, you might imagine that the elementary charge as a unit is not a suitable one. At this scale, we instead tend to write charge in terms of the unit coulombs, which is denoted by a capital C. 1 coulomb is roughly 6.24 times 10 to the 18 elementary charges. Equivalently, 1 elementary charge is 1.6 times 10 to the minus 19 coulombs. Given the force is in newtons and the distance is in meters, we typically express the constant K in units Newton meters squared per coulomb squared. In these units, its value is approximately 8.99 times 10 to the power 9. All in all, this gives us the magnitude of the force. But as force is a vector, we also need to know its direction. As we are considering the force experienced by charge Q1 due to Q2, the direction of the force is simply the direction from the charge Q1 to charge Q2. Let's start with a simple two-dimensional case and say that the charge Q1 lies at a point P1 and the charge Q2 lies at a point P2. We denote the vector from point 1 to point 2 as R12. The magnitude of this vector is the distance between our charges, and the direction R12 hat can be found by dividing R12 by its magnitude. Here is some working to show how these terms are calculated from the positions P1 and P2. As we said at the start, we already know whether the forces are attractive or repulsive through our values for Q1 and Q2. If Q1 and Q2 are both positive or both negative, the force on Q1 will point away from Q2, while if Q1 and Q2 are of opposite signs, the force will point towards Q2. You'll see that this result will automatically pop out upon calculating the force, which we'll do now. Alongside the force on Q1 due to Q2, we also want the force on Q2 due to Q1. If you apply the same working to this force, F21, you'll find that the magnitude is exactly the same, and that the only difference is the direction, which points exactly in the opposite direction of the force F12. This is because the direction r hat 2, 1 is always minus r hat 1, 2. Upon varying the values of the charges, the forces vary accordingly. It's worth mentioning that we can also extend all of this to 3 dimensions, where we simply replace the force and direction with 3D vectors. For visual simplicity, we'll keep everything 2D here, but the working is the same either way. But what happens when we have more than 2 charges in our system? If we introduce another charge Q3 at a point P3, we also need to write out the forces on Q1 and Q2 due to Q3, and vice versa. So now, Q1 experiences a force F12 due to charge Q2, and a force F13 due to charge Q3. These are both vectors which we can sum together tip to tail to find the total force on Q1. Likewise, we can do the exact same thing for charges Q2 and Q3. Though this gets rather complicated quickly, the principle is very simple. Just apply Coulomb's law to the interaction between each charge and every other charge in the system. If we want to get fancy, we can express the force on each charge Qi as the sum, denoted by a large sigma symbol, of the forces due to each other charge Qj, where the indexes I and j denote the charge label, and Nq denotes the total number of charges in the system. So, in essence, Coulomb's law describes the force experienced by each charge due to each other charge around it. Now, you probably have a few questions about this whole situation. In the last lecture, we spoke about charge as a fundamental property of nature, which is carried by tiny particles called electrons and protons, which alongside neutrons make up more or less everything around us that we know about. So far, we've been talking about these ideal charged spheres, which we're actually pretending are point charges. You might be wondering why we don't just use electrons or protons in this example. Technically, Coulomb's law does still apply to them, but only as part of a more complex picture, which includes quantum mechanical effects. Regardless, Coulomb's law remains very accurate for many experimental scenarios at the macroscopic scale, where objects are made up of electrons, protons, and neutrons. These charged spheres we speak of are typically made of a conducting material, with a huge surplus or shortage of electrons, which results in the spheres having net negative or net positive charge. In our scenario with charged spheres, a limiting factor we need to consider is the radius of each sphere, as if it is too large compared to the distance between the spheres, the charge distribution within each sphere complicates the interaction. So overall, we say that Coulomb's law holds when the distance between the spheres is much greater than the radii of the spheres. You might also be wondering why we care so much about this specific scenario using charged spheres. In the following lectures, we'll see that this example is essential for dealing with other geometries such as wires and charged plates, which we will later use to build circuits from. You probably also wonder where the expression for Coulomb's law comes from. Why does the force depend on 1 over r squared? And what does this constant k actually mean? Originally, Coulomb's law was demonstrated experimentally, where the expression matched empirical data on the forces between 2 charged spheres, and the constant k was calculated from this data. However, it was later demonstrated that Coulomb's law can also be derived from Gauss's law, which is a far more general expression for dealing with situations like this. Gauss's law is way beyond what we've learned so far, and we won't cover it in this lecture series, but we can take the results from it to understand a little more about our expression. It turns out that our constant k can be more generally written as 1 divided by 4 times pi times epsilon naught, where epsilon naught is the permittivity of free space. Epsilon naught is just another constant, but it has a far deeper significance, It is the measure of how easily electric fields can form in a vacuum. Vacuum is just a fancy word for empty space, and we'll talk about electric fields in the next lecture. But for now, you can think of epsilon naught as the constant deciding how large the force between two charges is in empty space. This constant epsilon naught has a value of roughly 8.85 times 10 to the minus 12 coulombs squared per newtons per meter squared. If you are curious about the origins of this constant, it is worth looking up the work of James Clerk Maxwell, who generalized electricity and magnetism via the Maxwell equations, which include Gauss's law. But where does this 1 over 4 pi come from? Well, if we rewrite our expression with our new definition of k, we find that our denominator becomes epsilon naught times 4 pi r squared. For those with a keen eye, you'll notice that 4 pi r squared is the surface area of a sphere, with a radius equal to the distance between our two charges. This is no coincidence. Essentially, you can think of the strength of the force weakening as it spreads out in all directions, and the surface area of a sphere represents how much area it spreads into. Now, there's one more nuance to all this that we need to mention. So far, we have assumed that the space between our charges is completely empty, or is in other words, a vacuum. But what happens if our charges aren't in empty space? If this is the case, then the force between our charges will be reduced further. We account for this with a relative permittivity factor epsilon r, which is also known as a dielectric constant. On a side note, we can also define the effective permittivity as epsilon naught times epsilon r. The relative permittivity for air is 1.006, meaning the strength of our force is almost the same as in empty space. However, for a medium like dried concrete, the relative permittivity is around 4, so the forces are 4 times smaller, while for water it is around 80, so the forces are 80 times smaller. The reason the force is diminished in these mediums is because of the many charges that already exist here, which cancel out or screen our charged spheres to some extent. So, all in all, we have a system for figuring out the force between two or more charged spheres. To summarize our findings, Coulomb's law describes the electric force between 2 point charges, and is written as F equals K times Q1 Q2 over R squared times R hat, or, equivalently, F equals Q1 Q2 over 4 pi epsilon naught R squared times R hat. The force is attractive for opposite charges and repulsive for like charges. The direction of this force is captured using the unit vector r hat. In multi-charge systems, we calculate the force on each charge due to every other charge, and sum the force vectors to get the total force. Epsilon naught is the permittivity of free space, while epsilon r is the relative permittivity of materials. We can consider charges in a medium other than free space by adding a prefactor 1 over epsilon r to our expression. With this considered, we now know how to calculate the force between two or more charges. For systems of, say, 10 charges, we can manage this without too much trouble. But as soon as we introduce many more charges, perhaps 1 billion, as in a metal wire, the calculations quickly become unreasonable. What we need is a more general way of thinking about how charges influence the space around them. This leads us to the concepts of the electric field, an invisible structure that surrounds each charge, mapping out the force that any other charge would feel at every point in space. We shall discuss this in the next lecture.